So in this problem, we are given a system of springs and mass m is connected to this system, and we have been asked to find the angular frequency of oscillation when the system is left from rest. Okay, in such cases, first what you have to do is to identify which all springs are in parallel, just like in resistors, and which all springs are in series. Now observing here, we get these two springs are in parallel, these two and those two are in parallel connection, or they are parallel to each other. And what happens because of this? When this mass causes the system to stretch, the springs in parallel will stretch by equal amounts simultaneously. So just considering this small two strings as springs, you find that if this portion extends by x, each spring will extend by the same amount equally, that is x. So the restoring spring force will be kx and kx. Therefore its sum 2kx will be the effective spring force. And if you don't care about these two springs and you just want to compress them into one single spring, then it will be similar to a situation where a spring constant 2k is being pulled by a distance of x. Okay, now the first step is over, that we have identified which all springs are in parallel and which are all in series. Now the second step is to simplify the problem. Now I will redraw the diagram here. These two springs we understood they are in parallel. So the net spring constant becomes the sum of the two spring constants. So let me write it down here. K effective in case of K effective in case of parallel connection will be equal to K1 plus K2 plus K3 plus etc. Now if you notice, this is similar to the formula for resistors in series and similar to capacitors. So springs in parallel behave like resistors in series. Now it is quite assumable that in series 1 by K effective will be equal to 1 by K1 plus 1 by K2 plus etc. Now how did this come? It's a bit long and lengthy to derive this, so I will not be deriving it in this video, but you just notice that when springs are connected in series, they behave like resistors in parallel or capacitors in series. Okay, now having understood these two very important formulae, we can apply this in this problem. So K and K will add up, since they are parallel, to be 2K. This 2K will remain as it is, 2K, and these two will again add up to be 2K. Now I will keep the remaining two springs in the ends as it is at K and mass M. Notice we are still observing the initial system, we are just simplifying the system. It has not yet expanded and harmonic motion has not yet started. Now these three springs 2K, 2K, 2K are in series. So what we should do is to find the effective spring constant. So we will be able to simplify three springs into one. 1 by K effective will be equal to 1 by 2K plus 1 by 2K plus 1 by 2K. Now the sum will be 3 by 2K. Therefore the sum of these three spring constants will add up to be 2K by 3. I hope this is clear. Now I will just erase this diagram and instead we will replace these springs with a single spring of constant 2K by 3. Now observe, these three springs are in parallel, so their spring constants add up and we get a single effective spring constant which is equal to K effective equal to 2K, that is K plus K, 2K plus 2K by 3, which will be equal to 6K plus 8. So 8K divided by 3. Now this is the effective spring constant. Now we know that omega will be equal to root of K by M. So that will be equal to root of effective spring constant 8K by 3M. Now this is our final answer.